Hello, students, and welcome to this educational guide on the fascinating world of electricity, which is a cornerstone of your CBSE Class 10 physics syllabus. I mean, think about it. Electricity silently powers our modern world, from the device you're using right now to the lights that illuminate your home. But how does it all work? Let's embark on a journey to uncover its secrets. So, our exploration of this chapter is structured into clear, logical modules. We will begin with the absolute fundamentals, electric current and potential. Right. Then we'll delve into the crucial laws that govern circuits, and finally, we'll connect theory to practice, exploring real-world applications and safety measures. And these are vital for all of us to know. Our learning objectives for the session are pretty straightforward. By the end, you will be equipped to define electric current and potential difference. You'll thoroughly understand Ohm's law, analyze resistors in series and parallel, and confidently calculate electric power and energy. Let's begin. First, what exactly is electric current? Well, in simple terms, it's just the rate of flow of electric charge through a conductor. We measure current in a unit called amperes, okay, and that's abbreviated as A. The governing formula is I equals Q divided by T, where I is current, Q is the net charge, and T is time. Now, an important distinction to make is the direction of current. You see, by convention, we consider the direction of current to be the direction of flow of positive charge. However, in metallic conductors, it's the negatively charged electrons that actually move. So the actual electron flow is opposite to the direction of conventional current. Weird, right? So what gives these charges the impetus to flow? That force is the electric potential difference, or as it's more commonly known, voltage. Yeah, imagine it as the electrical pressure that pushes the charges through a circuit. It's defined as the work done to move a unit charge from one point to another. Its formula is V equals W divided by Q. And we measure potential difference in volts using a device called a voltmeter, which is always connected in parallel across the 2 points you're interested in, okay? This brings us to the most fundamental law in this entire chapter, Ohm's law. It establishes this simple yet profoundly important relationship between voltage, current, and a property called resistance. Ohm's law states that the potential difference, V, across a conductor is directly proportional to the current, I, flowing through it, provided that the temperature and other physical conditions remain constant. That's a key part. Mathematically, we express this as V equals I times R. This linear relationship, it's just elegantly demonstrated by a VI graph. For a conductor that obeys Ohm's law, this graph is a perfect straight line going right through the origin. The slope, or gradient of this line, yep, that directly gives us the value of its resistance, R. Let's apply this with a practical example. A heater draws a current of 4 amperes when connected to a 220-volt source. So what's its resistance? By rearranging Ohm's law, we get R equals V divided by I. Substituting the values, that's 220 volts divided by 4 amperes, which calculates to 55 ohms. See, it is truly that straightforward. But what is this resistance on a deeper level? It's the inherent property of a material to oppose the flow of electric current. Several factors determine a conductor's resistance. Firstly, its length. A longer wire offers more resistance. Makes sense. Secondly, its cross-sectional area. Right. A thicker wire provides an easier path, so it has less resistance. A great analogy is a water pipe. A wider pipe lets more water flow with less opposition. The third and maybe the most important factor is the material itself. This intrinsic property is quantified by its resistivity, symbolized by the Greek letter rho. Yep. Materials like copper and silver have very low resistivity, making them excellent conductors. On the other hand, materials like glass and rubber have extremely high resistivity. Wow, that makes them insulators. And lastly, temperature affects resistance. So for most metallic conductors, resistance increases as they get hotter. The formula that ties all this together is R equals rho multiplied by L divided by A. Now let's explore how circuits behave when we combine multiple resistors. The first configuration is a series connection, where resistors are connected end to end, creating a single undivided path for the current. A defining feature of a series circuit is that the current stays the same through every single component. The total or equivalent resistance is found by just summing the individual resistances. SR equals R1 plus R2 plus R3 and so on. Let's apply this to bulbs in series. Since the current is constant for all of them, their brightness will depend on their power dissipation, which is given by P equals I squared times R. Now this means a bulb with a higher resistance will dissipate more power and, yep, it'll glow brighter in a series circuit. This is a really common point of confusion, so just take a moment to absorb that. Let's clarify with a solved problem. We have two bulbs. One is 100 watts, the other is 60 watts, both for a 220 volt supply. If we connect them in series to that same 220 volt source, which one will be brighter? Well, the first step is to calculate the resistance of each bulb using R equals V squared divided by P. You'll find that the 60 watt bulb has a higher resistance than the 100 watt bulb. Okay, since they're in series, the same current flows through both them. Therefore, the bulb with the higher resistance, the 60 watt bulb, will dissipate more power and, yep, it'll glow brighter. The second type of connection is the parallel configuration. Here, the terminals of all the resistors are connected across the same 2 points, providing multiple paths for the current to flow. The defining characteristic here is that the voltage across each parallel component is exactly the same. The total current from the source splits, right, with a portion flowing through each branch. To calculate the total resistance in a parallel circuit, we use the reciprocal formula. 1 over Rp equals 1 over R1 plus 1 over R2, and so on. A crucial outcome of this is that the total equivalent resistance in a parallel circuit is always less than the value of the smallest individual resistor. You see, this principle is exactly why our homes are wired in parallel. It ensures that every appliance gets the full mains voltage and can be operated independently. In practice, a lot of circuits are mixed with sections of both series and parallel connections. The strategy to solve these is just to simplify the circuit step by step. So first you identify any distinct parallel groups and calculate their equivalent resistance. Then you can conceptually replace that entire group with a single equivalent resistor. Okay, and that new resistor will now be in series with the rest of the circuit. You just keep doing that until you're left with a simple series circuit. Have you ever held your hand near a working light bulb or an electric iron and felt that heat? That is a direct manifestation of the heating effect of electric current. Yeah, a phenomenon also known as Joule heating. Whenever current flows through a conductor that has resistance, right, some of that electrical energy is inevitably converted into heat energy. This effect is described perfectly by Joule's law of heating. It states that the amount of heat produced, H, is directly proportional to 3 factors, okay? The square of the current, I squared, the resistance, R, and the duration for which the current flows, T. This gives us the formula H equals I squared times R times T. This heating effect is harnessed in so many practical applications. In electric heaters and irons, a coil made of a high resistivity alloy like nichrome is used specifically to generate a huge amount of controlled heat. In an incandescent bulb, a tiny thin filament of tungsten is heated so hot that it glows white hot to produce light. And most importantly, this effect is the working principle behind a safety fuse. That's where a special wire with a low melting point just melts and breaks the circuit if the current surges, protecting our valuable appliances and preventing fires. Now let's shift our focus to electric power. In physics, power is just the rate at which work is done or energy is transferred. So accordingly, electric power is the rate at which electrical energy is consumed or dissipated in a circuit. Yeah, its SI unit is the watt, named after James Watt. The primary formula for power is P equals V times I. Power is just the product of potential difference and current.
By combining this primary formula with Ohm's law, we can get two other extremely useful expressions for power. P equals I squared times R and P equals V squared divided by R. Being familiar with all three forms and knowing which one to use for a problem, well, it can make your calculations so much quicker and more efficient. When you get your monthly electricity bill, you'll notice the energy consumed isn't measured in joules. For commercial purposes, a much larger, more practical unit is used, the kilowatt hour. Right. It's often abbreviated as kWh and is simply called a unit of electricity. 1 kilowatt hour is the energy consumed when an appliance with a power rating of 1 kilowatt runs for 1 hour. And for conversion, 1 kilowatt hour is equal to 3.6 million joules. Wow. Calculating the cost of energy is a very practical and useful life skill. The process is logical and simple. First, convert the power from watts to kilowatts. You divide by 1000. Next, multiply this power in kilowatts by the number of hours the appliance is used. That gives you the total energy in kilowatt hours. Finally, you just multiply that kWh value by the tariff rate, the cost per kilowatt hour, to get the final cost. While electricity is indispensable, it must be handled with respect and caution. Following basic safety measures is non-negotiable. Always use properly insulated tools. Make sure your hands are dry before touching any switch or appliance. Safety devices like fuses and miniature circuit breakers or MCBs are essential to protect circuits from overloading. Also, the practice of earthing or grounding gives a safe path for fault current to flow to the earth, which can be a literal lifesaver. The wiring in our homes is a perfect real-world application of parallel circuits. This design ensures every appliance, from a lamp to a fridge, gets the standard means voltage and can be switched on or off without affecting any other device. For safety and efficiency, household circuits are divided up. Separate circuits with thicker wires and higher rated fuses are used for high power stuff like air conditioners and geysers, while a different circuit is used for low power points like lights and fans. This slide here is a quick reference sheet, consolidating all the essential formulas we've covered, from Ohm's law to the formulas for series and parallel resistance to joules heating and electric power. This is an invaluable tool for a quick revision before an exam. Solving numerical problems. I know it can feel challenging sometimes, but a systematic approach makes it much more manageable. This flowchart gives you a clear step-by-step guide. First, read the problem carefully, identify what's given and what you need to find. Next, choose the best formula. Then make sure all your values are in the proper SI units before you substitute them in. Finally, calculate the answer and, if you can, do a quick check to see if the result seems reasonable. To prepare effectively, it's always a great idea to practice with questions from previous year's board exams. This helps you understand the patterns, the marking scheme, the difficulty, all of it. For example, a question from 2018 asks for the equivalent resistance when three 3 ohm resistors are connected in parallel. Using our formula, 1 over P equals 1 over 3 plus 1 over 3 plus 1 over 3, which sums to 1. So therefore, the equivalent resistance Rp is 1 ohm. Simple. Here is another set of solved problems for you to work through. Practice is absolutely key to building confidence and mastering this chapter. Okay? Take your time, understand the steps in each solution, and pay close attention to how the correct formulas are applied for different circuit types. Finally, we have a glossary summarizing all the key terms and definitions we've discussed. This, combined with your NCERT textbook, really forms the core of your study material. Yeah. And feel free to use the recommended video resources if you need to, visualize any of these concepts further. Thank you for joining this session on electricity. Remember, understanding comes from questioning and practice. So keep practicing, stay curious, and always handle electricity with the care and respect it deserves. Now, here's a question we'd like you to think about. Considering